Okay, I'm gonna get going here on this second lecture of the day, second and last lecture of the day. So what Andy did for the last hour or so is give a really nice and concise overview of the theory underlying spatial capture-recapture. Now, what we're doing in such a short form is trying to give you all an opportunity to learn how not only how spatial capture-recapture works under the hood, but also give you the opportunity to learn how to actually fit these models and process your data and get to the point where you can generate estimates of density, abundance, detection, and space use, and all the cool things you can do with spatial capture-recapture. And the way we're going to do that is to use this package oSCR, or we just call it oSCR. So what I'm going to do over the next, probably just over an hour, is try to link all of those key concepts that Andy talked about, relate them explicitly to the structure and functionality of the R package oSCR. So hopefully to the point where you're all able to fit a basic model in this package by the end. So just to reiterate what Andy said, the oSCR is an R package that really came out of some of the work we were doing a few years ago now. And really we think of it as a complementary package to some of the ideas we spoke about in this R package, this review paper that was out a couple of years ago. We think of oSCR as being a flexible analytical framework for spatial capture-recapture modeling. Really, the key structure is that we have this multi-session structured likelihood built explicitly into the modeling. So it's transparent. We try and keep all of the code base in native R, so it is editable, and there should be an evolving code base as more and more people get to use it. That's our hope. The idea is that we want to build a community of contributors and a community of users where we have this community of people who are interested in applying these models, who can generate ideas, solutions, and potentially some code that we can integrate into the package. So here's a couple of links here. There's a listserv associated with the package and the email address if you want to ask questions. And we're a friendly bunch. But what we have done over the last, maybe this is the fourth year or maybe even the fifth year where we've been formally teaching spatial capture-recapture using this R package oSCR. So we've come to use it not only as a development of our research ideas, but also a framework within which we can teach spatial capture-recapture methods to people who aren't familiar with them. So a couple of things I want to make sure people are aware of. oSCR is one of several packages that are available to analyze encounter history data or spatially explicit encounter history data. It's an alternative, but not a replacement of the package SCR, spatially explicit capture-recapture, which is maintained by Mary Efford. It's an alternative, but again, not a replacement of Bayesian analysis. So lots of things that you might want to do that require Bayesian analysis. There's also some things you'd like to do that require likelihood-based analysis. And really this package is a likelihood-based package, which has some advantages. Speed, for example, sometimes. Model selection or multi-model inference can be a lot easier if you're using the likelihood-based approaches. So you can do model selection by AIC in a very straightforward and established way. You can specify models. If you've ever fit models using GLM or GLMM, you can really fit any kind of complex models using just the standard R formula notation. And we also have these kind of more advanced topics like least cost path modeling or resource selection function modeling that we built into the package that retain that ease of use, that user-friendly model specification. So the key technical features of oSCR are, like I mentioned before, this general modeling framework where we have this multi-session structure built in. And when we talk about multi-sessions, by session what we mean are spatial units or temporal units that we can consider somewhat independent. We also have these very explicit sex structured models or model specification. And essentially what the working core of oSCR is this multi-session sex structured likelihood. That's what we refer to the model as. It's really based on the ideas that Andy spoke about, these Poisson point processes for density estimation. We have built in these advanced features like the non-Euclidean distance functions for inference about landscape connectivity. And also we have the integrated telemetry or resource selection function models that give us inference about resource selection and space use. So essentially what in addition to being a teaching tool, what oSCR is also a package that's developing along with our collective active research. Okay, so I have provided this, I already provided these links in the Slack channel earlier on, and hopefully everyone's been able to download the package. But essentially the package is hosted on GitHub, so you can access it using these 2 lines of code here. And so we occasionally, usually round about workshop season, we push some changes to that, and we'll let everybody know if there's any major changes pushed to the GitHub, and recommend that you update the package accordingly. Okay, so let's jump into this workflow of oSCR. Every analysis that you'll do in the package involves the following few steps. First is formatting the sampling data, so that by sampling data I mean the spatial encounter history, so the detection information, but also the detector information, so where are your traps placed on the landscape. And there's also other information that you might have, like detection covariates. Was it on a particular day, or what habitat was your camera in, or what was the state of your cover board, things like that. So this is the information you take in the field. The second component, or the second step, is the definition and the formatting of the area of interest. So by area of interest, we mean the state space object. So what is the size of the state space? What is the resolution of the state space? And do you have any spatial covariates that you want to use to explain spatial variation and density? Of course, there's the key step, which is analyzing the data, or the model fitting step. And then getting from model fitting to inference or interpreting the models to the people who want to know what we find out, there's this fourth step, which is post-processing the model output. The things that you want to do for your thesis or for your paper or for your technical report. And each one of these steps has helper functions associated with it in order to make workflows repeatable and somewhat transparent and shareable. And because we're all users or contributors to Unmarked, the package Unmarked that's famously used for mixture models or occupancy models, we've tried to kind of model this workflow based on the Unmarked workflow. So if you're familiar with Unmarked or have ever used Unmarked before, what you'll probably find is that some of these steps may seem familiar to you, and even the functions may have similar names. Okay, so the first step in this workflow is formatting the sampling data. So just as a reminder, we have this spatially explicit observation model that Andy introduced, where you've got this kind of coin flip process where the probability of getting ahead is somewhat defined by where you live. So the probability of the detection is conditional on where you live. And that probability is defined here. I'm going to use this half normal detection function here. And the thing to recognize about this model is that there's some data components. So the Y's are the observations and the X's are the trap locations. So there's actually data built into this function. So what we want to do is find a nice way of collecting up all of that data and storing it in something analogous to a nice, neat data frame. We can think about detection covariates and things like that later on tomorrow. So the way we organize this sampling data is in something called an SCR frame. So a spatial capture-recapture data frame. You can think of it like that. So the first, if you're doing spatial capture recapture, essentially you'll end up with, as far as we've seen, you end up with two basic spreadsheets. The first spreadsheet is what we call the encounter data file, the EDF, and this tends to be a single data frame where each row is a detection. And each row has these key columns with capture information. So a session ID, what was the study area, for example. The individual ID, which individual was it that you captured, 1567325, or whatever the individual name is. Which occasion did you capture that or make that capture on? So was it day 1, day 2, day 3? And importantly, which trap did you make that detection in, or did you find that individual in? And you can also have you probably collect other information like sex. That's another thing. We don't necessarily require sex information, but sex is one that's often collected when you do capture recapture. So in fact, this is how data are typically organized if you go out and do a study. So let's pick up where we left off with the simulation study that Andy just spoke about. What I'm going to do here is set a seed so that my results are consistent with any of your results if you want to try and run these scripts. So by setting the seed, I'm kind of hardwiring a random number in so that we'll always get the same answers if we do some random things like the random uniform generation here. So this is just really, I'm just presenting again what Andy showed. What I'm doing is defining the limits of where individuals can live with this X lim and Y lim from 0 to 13. We're generating population size. We can calculate what the density is for that, or the expected density. We can generate some individual activity centers. We define the traps. And we can define the distance between traps and those activity centers. So here's one realization of what this code could produce. Each red dot is an activity center, the crosses are traps, and the big polygon, the big square, is the state space where those approximately 40 individuals can live. And then what Andy went on to do is define the parameters of the spatial capture-recapture model. So the detection probability 0.2, the value of sigma, and then generated this probability matrix, the number of traps, the number of occasions, and then this empty Y array, which is where we were going to fill with ones using this loop within a loop. So we're looping over individuals, then looping over traps, asking or tossing the coin and asking whether or not we captured it, knowing that this PMAT here, this probability matrix, is defined by distance between where the individual lives and where the traps are. So this is just exactly what Andy showed before. But the important thing to recognize is that this isn't how the data are typically organized. None of you, I guarantee, will go out and collect a 3D array of binary variables when you go out and do a study. So what I'm going to do is just use these few lines of code that I'm not going to dwell on. If you're really interested in how it works, you can check it out. But essentially, I'm going to take this 3D Y array, and I'm just going to convert. I'm going to ask, are these variables, these cell values, greater than 0? So I'm essentially just asking which ones are ones, and then wrapping it in a data frame. And then what happens is magically the EDF pops out. So essentially this is just giving me an index of which row, which column, and which slice there was a 1. And that just neatly turns into an encounter data file. So here we can see session 1. Well, this is just a single session model, so we only have one session. But the first row, individual 18, so the 18th row in the Y array, was captured in trap 4, the 4th column, in occasion 1, the first slice. And if you just follow that EDF, you'll get a full recovery of where individuals were captured and when. Okay, so that's the EDF. The TDF is the second object, which we refer to as the trap the trap deployment file. And this is a list containing a data frame for each session. So we're just dealing with a single session at the moment where we have a roper trap, and each column has some specific information we need. First of all, the detector name, and then the X and the Y coordinate of each detector. So essentially we have the spatial sampling reference point. So we know where every trap on the landscape is. Importantly, the EDF doesn't necessarily have all of the traps. If you take a look at this spider plot here, you can see there's lots of traps there, those big black circles where nothing was captured. So if you look in this trap column, you'll only see the traps where individuals were captured. That's why we need this trap deployment file, so we know where all the traps were, regardless of whether or not they caught an individual. So there can be other information that we can provide with this TDF, like trap operation information, whether the trap was on or off. So if you had a camera that malfunctioned 3 days into its 90-day stint, then you'd want to set the first 3 days as 1, and then the rest of the days as 0, to tell the package or tell the fitting function that it wasn't operational, therefore you can never have realized a 1. And we can also add trap level covariates, and we'll get into that a bit more tomorrow. Okay, so again, I'm just using the objects that Andy created in the last lecture, this traps object, and I'm going to create this TDF by just taking the coordinates, the X and Y coordinates, and also just giving each trap a name. So I'm just going to call it 1 to n row, which is basically the number of traps that we have. And then this is essentially what you would typically create or generate if you were doing a spatial capture-recapture study. So we have the trap ID and then the X and the Y coordinates. Okay, so here comes the first helper function, data to OSCR. And essentially what this helper function does is it links the EDF and the TDF together to make almost like a relational database. So we have a complete description of the spatial sampling, where things were and were not captured. So essentially what data to OSCR is doing under the hood is constructing the full 3D array as well as many other objects. So the thing to emphasize here is this point that it's extremely important, and probably one of the more common errors when using the package, to make sure that the names of the traps in the EDF are all contained within the names of the traps of the TDF. So they must match. And then once you use this data to OSCR function, it returns a bunch of useful objects. The most important for this context is the SCR frame, this, Spatial Capture-Recapture data frame. But then it also spits out a bunch of other data objects that might be useful for different types of analyses, like a Bayesian analysis, for example. Okay, so here, so this is what I'm going to do. I'm just going to introduce functions, give some context for why we need these functions and what they do, and then show you the code for how to, what you plug into the functions, essentially. So here we have an example of the data to OSCR function, and you can see that there's a few arguments that you have to fill in here. So the first is the EDF, so you supply this encounter data frame. The second is a list of the TDFs. And then these next few arguments are just basically telling the data to OSCR function which columns are associated with these particular required pieces of information. So SES call is the column that is the session identifier, or the study area identifier. ID call is just telling the function which column is the individual ID. The OC column is telling the function which column is the occasion column, and the trap column is telling the function which column is the trap ID. And then there's a few other, there's many more arguments in fact, but for our purposes here, I've just shown the ones that we need to fit a basic model. There's the sex column. If you did collect information about sex, you can tell the function which column that's in. K is the number of occasions, and N traps is the number of traps that we have in our TDF. And then once you run this function, data to OSCR, like I said, there's a few objects that are returned. What we want to do is just extract the SCR frame. So this line of code here will extract the SCR frame. Okay, so here's how we would apply this function using our simulated data. So I'm just going to keep using the simulated data that was introduced earlier. And as a reminder, here's that EDF that I produced earlier. So now we can see using this EDF how we would go around about setting the values for these particular arguments that are required by data to OSCR. So the EDF is the EDF object. The TDF is a list of TDFs, and the reason that's a list is because if we have a multi-session model, we need to provide a TDF for each session, which allows us to have different sampling grids or different sampling occasions for each of our sessions. And then we have these column identifiers. So the session column is column 1, the individual column is column 2, the occasion column is column 4, and the trap column is column 3. So I mixed these last two up on purpose just so you can see that you need to specify which column these particular pieces of information reside in. And we have 10 occasions in this particular simulation, and the number of traps is just the number of rows in the TDF object. Okay, so it's quite straightforward, but what's actually happening, what data to OSCR is doing is a bunch of different checks. Are your trap names identical between the EDFs and the TDFs? Is there dimension matches across all of the different parts of the data structure? So actually under the hood here, there's a lot happening. And this is essentially, if you get out of the data to OSCR step error-free, essentially you're in good shape to then go and do an analysis. Okay, so just to give you an idea of what's actually contained within this SCR frame, so just as a frame of reference here, I've called it SF, SCR frame, SF for short. So if I use this function STR, which is basically asking R to show me the structure of this object, and I've just set max level to 1 just to show me the contents without all of the inner contents of each object. You can see that there's 11 objects within the SCR frame. And what I've done is at the end of this slide, there's like a supplemental, there's a supporting information section in the slides that goes into detail about what each one of these objects are and why it's important and how it's defined. I'm not going to go into them here, but if you are interested in what all of these components are, you can go to the end of the lecture and see what they are. But essentially we have the important thing, which is a 3-dimensional array of 1s and 0s and the trapping information. And that's the key information we need to do a spatial capture-recapture analysis. Okay, so once we've got the SCR frame, that's the first step in the workflow. What we can start doing is summarizing our data now in a nice packaged and convenient way. And there's 2 ways we can do that, or 2 main summary functions. The first is just by typing the name of the SCR frame. It's going to give us some numerical summaries, how many individuals we captured, mean, maximum, and things like that. And the second is a visual spatial summary of the captures, so something similar to the spider plot that Andy showed earlier. So here's an example of the numerical summaries here. So I've just typed the words SF because that's the name of my SCR frame, and then OSCR will spit out these 2 summaries. The number of individuals, so I've captured 21 individuals in this study. The number of traps, I have 64 traps. 10 occasions. So these numbers should be clear to us because they're the numbers that we, first of all, the numbers that we set up in the study, and then the number of individuals captured. But then we have these other pieces of information that are less straightforward to calculate, kind of just using the raw data. So the average number of captures is for every individual. Well, what's the average number of times you captured an individual in any trap? And then the average number of spatial captures is for those that were captured in more than one occasion and more than one location. how many times were they captured. So we've got good numbers of spatial captures here. It's important for spatial capture-recapture that you have some individuals that are captured multiple times. And Gates is going to talk about that on Saturday, the idea of how we design spatial capture-recapture studies. And then also we have this MMDM here, which is the mean maximum distance moved. So if you take every individual that was captured in more than one location, calculate the furthest distance between the locations that they were captured and take the average over all those individuals, that's what the mean maximum distance moved is. Okay, so that's the numerical summary. And then what we can do is just throw the SCR frame object into a plot function, and plot is going to immediately recognize the class of this object, which is an SCR frame, and then it's going to produce this kind of spider plot type figure. And here we can see that you should be able to see 21 dots here, and then each color is associated with an individual, and then the colored lines link the dots, which are the spatial averages, same as the S's that Andy showed in the previous lecture, to the locations where they were captured. Okay, so that's how we process the sampling data, the encounter history data and the trap. The second thing we need to do, and it's an extremely important step, is to define the area of interest, or the state space as we've been calling it. So again, as a reminder of the model component in spatial capture-recapture, we essentially have this point process model that describes how individual activity centers are distributed in space. So you can see this is the mathematical kind of expression of that. And in this particular case, we just have a single parameter on the right-hand side of this equation. And that's reflecting this idea that we have a homogeneous point process, or we're assuming a homogeneous point process. But that's not necessarily the case. We can model the density at any given point as a function of spatially explicit covariates, and that would be a version of the inhomogeneous process. So here, just to orientate ourselves around some of the notation here, big S we typically use for the state space. So that's the area that we're interested in, and that area is typically a discretized representation of space. So I spoke about this, that we have to define some resolution of a fine mesh of points to approximate continuous space. And then little s with an I or a subscript, S subscript something, is typically the pixel centroid. So for this fine mesh, essentially each point represents a pixel on the landscape, and it's a summary of how many individuals live or are estimated to live in that particular pixel. And these pixels are our mathematical representation of all the possible activity centers, activity center locations on the landscape. So this has been mentioned a couple of times by myself and by Andy, but the state space definition is an extremely important part of spatial capture-recapture because it's part of the model. The state space is part of the model. It defines where the individuals that you captured can live, but also where all the individuals that you didn't capture can live. So essentially it defines the population of interest. And the thing to realize is that it's not just a convex hull around the traps that you set out in the landscape. It actually includes unsampled parts of the landscape. So every trap or every individual is exposed to a number of traps, and you don't have to live on top of a trap to be exposed to capture. By explicitly incorporating the spatial component, this idea of space use or movement, essentially we have to acknowledge that the state space must be larger than the grid of traps that we've laid out there. So the state space itself, there's some rules of thumb that are typically, so there's some rules of thumb that exist. So they should represent all the activity centers of all detectable individuals on the landscape. So any individual that is exposed to the trap should have its activity center included in the representation of the state space. And you can typically achieve that by specifying a buffer of a certain distance around the traps. And the rule of thumb is 3 to 4 sigma units around the traps. So that means your buffer will include all the activity centers of all detectable individuals. And then because it's a discrete approximation of space, what you also need to do is not just define the buffer, but you need to define what those pixel centroids are. So the resolution of the state space. And typically you want to specify a resolution that is about the estimate of sigma or below. Okay, so that's actually a little bit abstract, the idea that you should know the parameter of interest in order to specify the state space. What you're going to see in a few slides' time is there is some kind of iterative process of making sure that you have selected the right values for the state space, and that really boils down to doing some crude sensitivity analysis of whether or not your estimates are sensitive to the definition of the state space. Okay, so essentially the way we take this idea or this notion of a state space and formalize it for analysis is through the definition or creation of this SSDF object, which is a state space data object, or a state space data frame is what the SSDF stands for. And essentially what this is a list containing spatially explicit information for each session. Again, what we're doing right now is focusing on a single session. So essentially we have a list with one object within that list, and it contains a data frame that has at least these pieces of information. It's an X and a Y coordinate, and we have to give them these specific column headers or names, the capital X and capital Y. And then each of these, so we essentially have a data frame of coordinates, and each one of these coordinates represents a pixel centroid. And it's important to note here that the coordinates should be in the same units, the same spatial units as the traps that are contained in the SCR frame object. So there's an X coordinate and a Y coordinate. And now that we have this data frame, which is basically a spatial representation of all the points in the state space, that's when you can go and do things with that, like turn it to a spatial object and start manipulating it using external shapefiles or extracting values from rasters and things like that. That's the very minimum information that you should have for an SSDF object, the X coordinate and the Y coordinate. What you can also have is columns for spatially referenced covariate values. So a pixel, like elevation, for example, pixel specific elevation value, and these can be continuous or categorical. Essentially, we can add columns of covariates as long as we have complete spatial representation of that particular covariate. And then once you have these objects, you can start knocking out non-habitat, like parking lots or lakes, or the sea, like Andy showed in the Wolverine example. You can remove them either manually as conditional on particular values, or even using these kind of spatial manipulation functions. And in oSCR, there's actually two ways to create the SSDF object. The first is to create it manually. So if you define some buffer around traps, and then you can extract spatial covariates from the GIS layer, for example. But what I'm going to do is show how we can do that using the simulation data. So essentially what we can do is just create a data frame, a spatially referenced data frame with X coordinates and Y coordinates, and give it the class SSDF. And then essentially we have our SSDF object. So here's an example of doing that for the data we used for simulation. So in the simulation, we defined the area as an area going from unit 0 to unit 13 in both the X and the Y directions. So what I'm going to do is just create a data frame that has every combination of coordinates from 0 to 13 by a resolution of 0.5, by units of 0.5. I'm just going to put that into a list because we have a single session object here. We just need a list of one data frame, and I'm going to give that a class SSDF because I'm creating it manually. And then if I plot this object, the plot function is going to automatically recognize the SSDF class, and it's going to plot the state space object. So it looks spatial, but it's just a data frame of coordinates. The SSDF plotting function can also take, if you supply the SCR frame along with it, it's going to show you the trap locations on top of the state space. And then we can also even specify spider equals true, and it will give us a full description of all the data we're using in the analysis. So first of all, we have our state space, the square measure points. We have our trap locations, and we also have the captures in there. So it basically integrates the spider plot function into this state space plotting function. The second way we can create an SSDF object is using the make SSDF helper function. So essentially what we're going to do is use the characteristics of the SCR frame to construct the state space. Now, of course, we can't generate spatial covariates doing this, but there are functions that exist in oSCR to extract covariates if you have a state space object. So what we do is we use the make SSDF function where we provide an SCR frame, we define a buffer, and then we define the required resolution. And that will create an object of class SSDF, and that will be the state space that's created explicitly matching the SCR frame that we provided. So how does it work? Well, essentially by defining a buffer, essentially what you're going to do is create a buffer of a certain width around the traps that are contained within the SCR frame, and then you're going to specify the resolution, and what's going to happen is there's going to be a uniform grid of points, and then you're going to clip out a particular buffer within that buffer width of the traps. So here again is just this reiteration of the fact that the buffer and the resolution do have some rules of thumb associated with them, whereby the buffer should be at least 3 to 4 sigma units. The resolution should be approximately the value of sigma or below. And what we can do as a starting point is use the value that we have in the SCR frame, the MMDM, as a guide. So you can think of half of the MMDM as being a biased approximate of the sigma value. And here's the point I made earlier, where once you fit a model, what you want to do is make sure you change the values that you use to generate the state space, just to make sure that your parameter estimates aren't sensitive to the definition of the state space. And I'm going to come back to that in a second. So essentially I got to the point where I'd manually created the state space object, and using just a data frame and packaging that as a list, and then giving it a class. I'm using this class argument here to give it the class of SSDF. So there's actually a lot of flexibility in specifying or creating the state space object. But then typically what I do is use the make SSDF function to actually construct construct a state space using the characteristics of my trapping data, and in particular the traps themselves. So what make SSDF does is it takes your trap objects, makes a buffer based on your definition of a buffer, and then makes a regular grid of points using your definition of the resolution. And then there is another function in oSCR which is called extract covariates, where you can just provide a state space object and a raster, and it will go and extract all of the appropriate values for you. So you can do that kind of So I don't think you necessarily need to ever construct a state space from scratch like this, when there are options to construct a basic state space and extract spatial information from GIS layers, for example. Okay, so essentially what we have here is the state space that was constructed using the make SSDF, and then I've just plotted it using a buffer. I've plotted the state space object, the SCR frame, and I've specified the spider equals true, and then I have my spatial representation of my whole study system and the analytical framework within which I'm going to fit models. And just to give you an idea of what those two things look like, essentially just by specifying this square state space from 0 to 13 spatial units, I get this square thing. By using make SSDF, I get this thing that trims out any of the corners that are beyond a buffer width from my traps. So that's the only difference that you have there. But I'm going to come back to show you a nice feature of spatial capture-recapture using these two objects as an example. But the bottom line of this section is that we need to define the state space, and that state space definition typically requires specifying a buffer area and a resolution of that mask of points, that fine mesh. Okay, so here's a recap of where we got to, or what the workflow is. This first slide here is basically simulating data. So really just in a handful of lines of code, you can take this code base and go and change the values, change the trap arrangement, change the values of abundance or density, and do your own simulation study if you want. But this isn't what we'd end up doing in practice if we went and did a SCR study. In fact, what we'd end up with is just an EDF object and a TDF object, and as long as we knew which columns had the relevant information, essentially what we could do is just with these 3 lines of code, construct or format all of our standard spatial capture-recapture data into the data objects that we require for analysis. So we spent a long time working on this data to oSCR function to really get us from raw data to analysis ready data with all of the error checking in between. Okay, so the third step in this workflow is the fitting of models. So we've taken the data that we go out and typically collect in the field, we've converted it from these raw kind of traditional data spreadsheets that you would have in Excel to this working data object that's analysis ready for this particular package. Now, of course, what we want to do is fit some models and start doing inference. We want to estimate parameters of the spatial capture-recapture model. So to fit a spatial capture-recapture model using oSCR, we essentially use this fitting function oSCR.fit. So this is the core fitting function in the package. And again, it's a very simple function to use. What's under the hood is perhaps less simple, but in order to actually use this model or to fit a model, you just need to specify 3 things. The first is the model that you want to fit. So there's a list that you provide, which contains the 3 components of the model. You give it the name of your SCR frame, and you give it the name of your state space object. So essentially you provide the data, and then you provide the model that you want to fit. So this is very much in line with the GLM. You specify the model and you say data equals, or even if you've used unmarked before, the same idea. You specify the model, and then you specify where the data live. So let's start with this. So writing out is just like this. oSCR fit, you provide the model object, the SCR frame object, and the SSDF. So let's just go through each one of these arguments in turn. So when I say you need to provide or specify the model, essentially an SCR model has 3 components, or 3 core parameters that you want to estimate. There's density, there's detection, the P0, the baseline detection probability or rate, and then okay, yeah. So the first argument the fitting function wants is the model argument. So you want to specify the model, and as we saw in Andy's lectures, there are 3 of these core parameters that you want to estimate in a spatial capture-recapture model. The first is the density, The second is the baseline detection probability. So that's the height of the detection function. And then sigma, which is the scale of the detection function, or the distance over which detection declines. So these are the three most fundamental, or the three basic parameters that are in every spatial capture-recapture model. So using standard R notation, we can use the tilde-1 notation to say, I just want to fit an intercept-only model. But we can model all of these things as a function of any number of covariates. So if we have spatially varying covariates in the SSDF, let's say we have a column in our state space object called elevation, we can just put elevation in the density formula and model density as a function of elevation. Likewise, for P naught, if you have information about the habitat quality that a particular trap is in, then you can, and you have habitat in your SCR frame, you can just type the word habitat in that formula and model detection as a function of habitat. So essentially, this is standard R formula notation, and we build it, and because there's these three model components, we just package it up as a list. So that's the first argument, which is the model. The second is just the SCR frame, and then the third is the SSDF. So that's straightforward. So what we're going to consider just for today is the null model, SCR null. So essentially, we're going to assume homogeneous density. So we're just going to estimate one parameter, and that reflects the assumption that our expected density across the entire landscape, or in each one of those pixels on the landscape, is the same. We're going to assume that there's no variation in expected density. And again, using standard generalized linear modeling ideas, because density has to be a non-negative number, we fit a log linear model to ensure there's positive densities or non-negative densities. So when we actually get some estimates back, we're going to start to see that they might be negative, for example, and that's standard for a GLM type analysis. So here we're going to assume, like I said, that beta is just a fixed parameter, an intercept only parameter. So we're assuming constant density across the landscape. And that is to say that all pixels have the same expected density. Likewise, and this is going to follow through for each of the parameters. We're going to specify this tilde-1 notation. By saying tilde-1, we're specifying an intercept-only model. So again, if you fit a linear model in R and you did data tilde-1, you'd be estimating the mean of the data. So that's what we're going to assume for this first model that we're going to fit, is that everything is the intercept-only model. But the thing I want to highlight is that we're assuming some link functions here. So Andy spoke about the logit link for the detection probability. So I'm just mentioning it again here, that for, if you have counts, which you can have in spatial capture-recapture, so instead of having binary variables, detected or not, you can also have how many times did you detect an individual at a particular camera in a particular week. In that case, we would specify a log linear model, because we're not bound between 0 and 1. We're still bound at 0, but you can have to infinity counts. But then for the probability model, so the probability of the detection, we have this logit link function that ensures that your detection probability is bound between 0 and 1. And that's kind of written out explicitly there. And then the third component is the sigma component. Now, again, we have to realize or recognize or remember that this is a spatial parameter. So we can't have negative distances, but we can't have very large or very small distances. So what we want to do is have an analytical framework within which we can estimate parameters on one scale, but make sure that they make sense on the real scale, or the biological scale. So again, for sigma, we're going to fit models that use the log linear model to ensure, or the log linear link function to ensure positive distances, because we can't have negative distances. Okay, so I'm going to get into I'm going to get a lot more into a lot more detail about kind of different models that we can fit. For now, I just want to show you how we can fit a model and then what are the outputs from the model. So here I'm going to fit a model called SCR naught, and it's going to have a list where I have this tilde1 notation for each of the 3 parameters. I tell the model fitting function that my SCR frame is this thing called SF, and that my state space object is this thing called SS buffer. And then when you execute this line of code, you'll get some stuff here that tells you which model you're fitting, which likelihood function you're using, kind of a jokey thing to hold on tight because these models take a little while to run, and then the date, and then the parameters that you're estimating. So you can see here that we have this intercept only set of formula. And what we see is that we're just estimating an intercept for the detection model, an intercept for the sigma model, and an intercept for the density model. Okay, so that took about a minute to fit that model. So what we want to then do is start looking at the model output. So really fitting a model is just one line of code. Then what we want to do is start interrogating that model fit to ask questions about, okay, well, what have we learned? How do our estimates relate to the hypotheses that we were trying to test in the first place? Of course, there are none here because we don't have any covariates, but we can make a start at doing the interpretation of the model output. So if we just type the name of the model, so here I call this model SCR naught. If I just type the name of the model once it's finished running, I'm going to get this output. Now, apologies if you haven't used a GLM before. I think we had kind of determined that everyone was familiar with R and probably had fit a linear model at some point. So essentially, when I make reference to the GLM, I'm hoping that most of you are following me here. So this idea that, well, basically we constructed this output to look as similar to unmarked or GLM output as possible. So it doesn't look like a bunch of gobbledygook that you just don't understand or have never seen before. So what we have is some summaries about the particular model that was fit. So here's the model that you fit. This is how long it took, 1.13 minutes. The AIC associated with that model. So this is the thing that we'd use to rank different model formulations. And then we have this summary table where, again, we specified this intercept only model for 3 components. So we know that we're only going to get 3 estimated parameters back, the intercepts for each of these model components. So this is where it's important to remember that we're using link functions. So we have this P naught here, which is meant to be a probability, but it's a minus. And we have sigma, which is also a negative sign. And we have density, which has a negative sign. So none of these can be real in biological terms. But when we remember that these are all modeled on a linear predictor scale and we have to apply a back transformation, then we can start to do that and see what our estimates were on the biological scale. Okay, so that's model fitting. So just to update us on the, or update this evolving workflow. So what we'd have is an EDF and a TDF, and as long as we know which columns have the relevant information, we can pump those into the data to oSCR function, take our raw data, and turn that into analysis ready data. And we can create a state space object. And then from there, we can fit a model. So really 3 lines of code, if you don't consider the lines of code to read your data into R, you can fit a null model with it using 3 lines of code. So now let's move on to how do we interpret this model output and start talking about what it is that we found. Why have we fit this model in the first place? Just want to check the time here. Okay. Okay, so here we are. We have these estimates, all negative, and we want to talk about like actual density, actual probabilities of detection, and actual spatial scale of space use. So we could, by hand, using just by applying the link function that I spoke about earlier, and then doing some delta method stuff, transform all of these estimates onto the real scale, but that's not straightforward and it would vary depending on your application. So what we did was write another helper function here, which is called get.real. And the reason it's called get.real is it's basically a function that will get your real estimates back. And by real, what we mean is back onto the biological scale, the scale of which makes sense to the biologist fitting models and for the inference objectives. So again, this is a very simple function to use for the get real function. There's three arguments, or there's several arguments, but three main arguments. The first is the model. So you just specify the name of the model that you fit. The submodel or type of prediction that you want to make. So you can say, I'd like to predict the density component of the model, the detection component of the model, or the sigma component of the model. I'm assuming that everybody can see my floating red dot here. And then just like most predict functions, you can specify a new data object where you can provide values that you want to make predictions for. So you can use the structure of the data and the covariate structure of the data to make predictions about the density in a particular part of your study area, for example. Okay, so the first thing we're going to do is focus on this density component, remembering that this is a log linear model. So in order to get to density from your estimate, you would need to exponentiate this parameter. But we don't have to do that. We can use the getReal function. And what the getReal function is going to do is back transform your estimates onto the biological scale or the real scale. And it's going to provide you a standard error and your lower and your upper confidence intervals. So these are nice things to have when you want to make predictions. So our estimate of density was minus 2.77. If you were in your R console right now and you typed EXP, open parenthesis, minus 2.700, close parenthesis, the answer you'd get is 0.0672 and change. So essentially, we could very easily do this part, but recovering the standard error and the confidence bands or the confidence limits on these particular estimates isn't straightforward, and that's where the function really helps out. So in every pixel, so we'll just take you back to this output here, there's a little note underneath the summary table that says density intercept is the log of individuals per pixel. So you always have to remember that this density estimate is the expected number of individuals living on that pixel. And of course, it's less than 1 because there's not multiple individuals living in every tiny pixel on the landscape. So you can think of it as the landscape aggregate. Okay, so yeah, that's the point here, that the estimates are per pixel. But what we can use is the d.factor argument within the getReal function to scale that density estimate to something that might make more sense to a manager, for example. So if we're studying bears and our pixel resolution is 500 meters by 500 meters, the reserve manager doesn't want to know what's the number of bears per 0.5 by 0.5 pixel. Maybe they're more interested in knowing how many bears per kilometer squared. It's something a bit more reasonable or intuitive to kind of, yeah, something more intuitive essentially. Here in a simulation context, it's hard to be intuitive because there's arbitrary spatial units, but as an example, what we used was 0.5 by 0.5 pixel resolution. So let's say, for example, a unit is a kilometer. So we can say that the pixel resolution in our simulation study was 500 meters by 500 meters. So if we take 4 of those, that equates to one square unit on the landscape, or one square kilometer. So what we can do is use this d factor equals 4, and essentially what that's going to do is multiply your density to a scale that's more intuitive or more relevant to your study system. So again, if you did 4 times EXP open parenthesis minus 2.7, you would get this number here. But what's nice about the get real function is, again, it produces the associated uncertainty, the standard error, and the lower and upper confidence intervals. A nice thing about this function is that you can also compute total population size. So if you think of every pixel, the density estimate is the expected number of individuals at every pixel, then you know you have a certain number of pixels on the landscape. So if you add up all of the expected densities of all of the pixels, then essentially you should have your expected number of individuals on the landscape, or your expected abundance. So what we can do is use this D factor argument and just ask, well, how many pixels are in my state space? So here I've said, how many rows are in this state space object, which is the same as asking how many pixels are in my state space. And I'm going to use that as the D factor, the density factor. And what I'm going to end up with is an estimate of the expected total number of individuals, the expected abundance in that landscape. So the bottom line here is that you can use the D factor to scale your estimate of per pixel density to any spatial unit of interest, including total abundance. Okay, so here's where I want to make the point about the estimate, or whether or not the estimate should be sensitive to your definition of the state space. So here are the two state space objects that we created before. One was the square one, and one was the buffered one. And the only difference here is that there's some extra pixels in the square state space. So let's see what difference that makes. Oh, there's an error in this slide here. So n row of SS buffer is 645. So there's 645 pixels in the buffered area. And there's 724, I think, or 725 pixels in the square buffer. So there's more pixels in one than the other. So my question here is whether or not we get different estimates of the parameters of interest if we use these two different these two different definitions of the state space. So what I do is I fit the model, exactly the same data object, but with two different state space objects. This one here, the square, and this one here, the buffer. And what difference does it make? Well, we can look at the output of the buffer. This is what we've been looking at already. We estimate there's 43.34 individuals on the landscape. Now I'm going to look at the output from the square state space. And if I just toggle back and forth here, you'll see that the parameter estimates here, if you focus on where my red dot is, actually nothing at all changes. The estimates of the parameters of the model are identical. What does change though is it took a little bit longer to fit the square state space model. That's because there was more pixels, so there's more computation happening. But importantly, what happens is that there's more individuals estimated to be in the square state space. And this raises a really nice point here, is that density should actually be insensitive to the state space. If you define the state space correctly, you can go larger and larger and larger. And because the thing you're trying to estimate is the per unit expected number of individuals in a pixel, then you can go larger and larger and larger. And because there's no information out there, your estimate of density should remain the same. And you can see that's the case here. So we have the per pixel estimate of density is identical between the two state space buffers. But then if I compare the abundance estimates, essentially what happens is there's more individuals in the, I've named those the other, I'll correct these slides and upload them again, but this should be the other way around, where because there's more pixels in the square state space, then essentially there should be more individuals. So we see some apparent sensitivity, but that apparent sensitivity is expected behavior. If your state space is larger, the density can be the same, but the number of individuals that you see is going to be more, or you expect to be there more, because there's just more area. Okay, then we can go through exactly the same process. So I focused on density there, but what we can do is just specify det instead of dense. So you'll see here that I was specifying dent to predict from the density model. Now I can specify det and predict from the detection model, and then I get an estimate of that baseline detection probability on the probability scale. So before, the estimate was minus 0.876. It was on the linear predictor scale. Using getReal gets us back onto the probability scale, and we have this is the probability of detecting an individual at its activity center on a particular occasion. And we can do exactly the same for sigma. So if we want to predict, if we want to get the actual value of what sigma is, rather than its linear predictor scale value, we can use the getReal function and specify type equals sigma, and then we have the estimate of sigma, which is 0.5 spatial units in this case. Again, the nice thing about getReal is that we have this associated uncertainty that gets computed along with it, which is tricky to do on a case-by-case basis. Okay, so essentially all of this analysis happened on simulated data. So what we can do, just out of interest, is see how we did at recovering the estimates of the SCR of the data that we simulated. So we simulated data where the expected number of individuals was 40, and our estimate in the end, when we analyzed the data that we simulated under a situation where there was 40 individuals on the landscape, was 48. But you can see that our confidence bands have 40 within them there. Likewise, our truth for the detection probability was 0.2, and our estimate here was 0.29. This time our confidence limits didn't include the true value, but this is just one realization of this particular simulation. And then the estimates of the spatial scale was 0.6. You see our estimate is 0.5. And our confidence intervals have 0.5 within them. If I did this 100 times or 200 times or 300 times, and I took the average estimate after simulating multiple data sets, what we'll see is that there's no bias in our ability to estimate, and all of this is stochasticity from the realized data. Okay, so the point of this hour really, or a little over an hour, was to try and to take the information that Andy provided in that first hour, this theoretical background for spatial capture-recapture, and then embed it within an analytical framework, or specifically within an R package that allows for really quite easy analysis of spatial encounter history data, hopefully using what seems like a logical workflow, a workflow that matches the data that we collect in real life, and then the models that are, the biology that we think give rise to the data that we collected. This involves taking your raw data, creating a SCR frame, a spatial capture-recapture object, generating a state space, so explicitly defining the state space object through defining a buffer and a resolution of that state space, fitting the model using the fitting function, specifying which model you want to use and the data you want to use to analyze the data, and then the prediction step, which is basically taking the model output and then deriving or getting estimates on the biological scale, which are in line with the inference objectives of the study.